Many phenomena that we're interested in exhibit randomness. We may see behavior that's a little different, or maybe a lot different, every time we witness the phenomena. When this behavior is represented with quantities, we say that the quantity is measured with a random variable. A random variable is a variable whose value can take on one of several realizations, and each realization is associated with a likelihood of occurrence. Say you're a quality control engineer at Duff Brewery, and you inspect cases of beer for defects. Such defects could include misplaced wrappers, scuffs on the bottle, incorrectly applied caps, and so on. Not every case of beer has the same number of defects. Therefore, the number of defects in each case would be a random variable. Several realizations of defects are possible, and each has a likelihood of occurring. Random variables typically are defined with capital letters, and then particular realizations of those random variables are given as lowercase letters. For example, we could define a random variable, capital Y, as the number of defects witnessed in a case of beer. Lowercase y would be a possible value that random variable y could take on. For example, 0, 1, 2, and so on. Random variables come in discrete and continuous varieties. A random variable that can take on discrete values is naturally a discrete random variable. This is often a random variable that is measured as an integer, much like the Duff Brewery defect problem we discuss. Defects are measured in the form of integers, as we can't view 2.73 defects on a beer bottle. But a discrete set of realizations don't necessarily have to be integers. For example, if an electronics manufacturer produces resistors that are either 0.75 ohms, 2 ohms, 3.2 ohms, or 5 ohms, a random variable might measure the ohm output of a randomly chosen resistor, and the realizations would be one of those four discrete values, some of which aren't integers. A random variable that can assume any value contained in one or more intervals is called a continuous random variable. There are a presumably infinite number of realizations of a continuous random variable, as there are infinitely many values that lie between 2 points on a continuous number line. For example, random variable x might measure the fill in ounces of a beer bottle filled at Duff Brewery, as fill in ounces would generally not be a discrete measure, but rather measured on a continuous number line. We're going to be talking about discrete random variables in this unit. The probability distribution of a discrete random variable lists all the possible values that the random variable can assume, along with their corresponding probabilities. The probability distribution of a discrete random variable is also commonly referred to as the probability mass function, though I generally use probability distribution. The notation for the probability of a realization of a discrete random variable capital Y is shown on the screen. We say that there's a probability that random variable capital Y takes on a realization lowercase y. When thinking about probabilities of a particular random variable, the notation is slightly different than the events that we covered in the discussion of probability rules. Events often described qualitative observations. For example, event R described a random card being drawn from the deck of cards is a red card. That's a qualitative kind of occurrence. With random variables, our event is random variable y taking on the value little y, a little different way to think about the same thing. The two properties of a probability of a discrete random variable are the same that we discussed previously. The probability of any particular realization of a random variable must be between 0 and 1, inclusive of 0 and 1, and the sum of the probabilities of each realization is 1. Back to our Duff Brewery example. Say that we looked at a sample of 800 cases of beer and found anywhere from 0 to 5 flaws in each case. Random variable y is defined as the number of defects witnessed in a case of beer, and lowercase y takes on the values 0, 1, 2, 3, 4, and 5. We take the relative frequency view of probability in describing the likelihood of each realization by counting the number of flaws in each case. For example, 296 of the cases had no flaws, so the probability that y equals 0 is 296 divided by 800, or 0.37. The table and the bar graph illustrate the distribution of random variable y, as they list all possible values that the random variable can assume, along with their corresponding probabilities. There are many problems for which we wish to calculate the probability that an observed value of y will be less than or equal to some value y0. In such a case, we use a cumulative distribution. This is represented as the probability of y less than or equal to y0 which is the sum of probabilities of each realization of y from the lower bound of realizations up to and including y0. With a discrete random variable, such as the number of defects in a case of beer, the cumulative distribution is simply the cumulative frequency. On the vertical axis is the probability that y is less than or equal to little y. For example, the probability that there are fewer than 3 defects is the probability that there are 2 or fewer defects, as fewer than 3 doesn't include 3. The probability is 0.86, or 86% of realizations of the random variable are less than 3 defects per case. When we're describing the central tendency of a discrete random variable, we often use the mean, or its fancier term, the expected value. We use the notation E of y, or the expected value of y. What do we mean by expected value? It's a value that we would expect to observe from the random variable on average. It has a similar kind of construction to the calculation of the mean that we discussed previously. Recall that we said the mean of a population was the sum of all observations divided by capital N, the total number of observations in the population. In this calculation, we assumed that each observation was equally likely. Any observation was just as likely as any other observation in the population, each occurring with probability 1 over n. In a sense, we were taking a weighted sum of the observations, multiplying each one by the likelihood of their occurrence 1 over n. With the expected value of a discrete random variable, we don't use equally likely probabilities of each individual observation. We take a weighted sum using the probability that each realization occurs. That is, we multiply the realization by the probability that that realization occurs, and we sum across all realizations. Let's calculate the expected value of the number of defects per case of beer from the Duff Brewery. The expected value of y is 0.37 times 0 plus 0.31 times 1, and so on. The expected value, then, is 1.15 defects per case. That is, on average, we expect to observe 1.15 defects in each case. We pair the expected value with a variance calculation to find a measure of dispersion for the random variable. The variance has a similar form as what we've seen previously. Generally, we measure dispersion as the squared difference between the individual observations and the mean of observations. Here we find the expected value of the squared difference between the random variable and its expected value. That is, the expected value of y minus mu quantity squared. We use the FOIL method to expand y minus mu quantity squared to y squared minus 2 mu times y plus mu squared. We carry the expected value operation through all the terms. We said y could take on several realizations. Can the number 2 take on several realizations? No, it's a constant 2. So the expected value of 2 is just 2. We can bring it outside of the expectation. How about mu? The mean of the probability distribution doesn't change. Its realizations are uncertain, but its mean is constant. So what's the expected value of mu? Just mu. Therefore, we can rewrite our expected value as the expected value of y squared minus 2 mu times the expected value of y plus mu squared. We saw previously that the expected value of y is mu. So 2 mu times the expected value of y is 2 mu times mu, or 2 mu squared. Negative 2 mu squared plus mu squared leaves us with negative mu squared. You'll see the general calculation of the variance of a random variable written a slightly different way as the expected value of y squared minus the expected value of y quantity squared. The expected value of y squared is the value of each individual realization squared multiplied by the probability that that realization occurs, summed across all realizations. Therefore, the variance of a discrete random variable is finally shown on the screen. Of course, if we prefer to think about dispersion in the units of a random variable rather than squared units, we can take the square root of the variance to find the standard deviation. For our Duff Brewery problem, we find the variance by squaring each realization, multiplying it by the probability that each realization occurs, summing that up across all realizations, then subtracting off the squared expected value. The variance would then be 1.41 defects squared. The standard deviation would then be 1.19 defects. Let's take a look at another quick example. Say that you're an analyst for the city planning department for a large city. When it comes to preparing for winter weather, decisions aren't made with a dart and a dartboard. You're going to take a look at previous snowfall amounts, to, in some way, forecast the winter weather supplies, such as salt and sand for city streets. Looking back on a few years, we see the distribution of snowfall amounts on the screen. Random variable x measures the number of inches of snowfall in a year. For example, the probability that x takes on the value 3 inches is 0.09. That is, 9% of years have 3 inches of snow. We can also have a look at the cumulative distribution. For example, we conclude that 3/4 of all years have 2 or fewer inches of snowfall. The expected value of snowfall in a given year is 1.67 inches, and the variance would be 2.22 inches squared, or the standard deviation is 1.49 inches. Note that the two distributions we discussed here, beer case defects and snowfall amounts, didn't follow a functional form. We found their probability distributions based on observation. We'll continue our conversation about discrete random variables with random variables that follow a particular functional form. And for all the probability problems that you'll encounter in this class, you must define the random variable. State explicitly the random variable of interest and what it describes, such that it's much easier to find the probability of a particular realization of that variable. For example, we said random variable x was the number of inches of snowfall in a year. We must explicitly state this variable.